Hi everyone, and welcome to the lecture on probability. This is an introduction to probability terms, and we're actually going to spend a lot of time on probability. And the reason is because the goal of statistics, ultimately, is to use a little bit of information to decide what's going to happen in a big group. Use a sample to decide what's true about the population, or use what happened in the past to help us decide what might happen in the future. And to do that, we need to have some idea of how likely things are to happen. And we're going to start probability in chapter 3. But please don't be intimidated. This section is incredibly heavy with terminology and symbols, but I have to give you the vocab before we can start speaking the language. So just try to hang on. The notes are on my website, and if you need any help, let me know. So first, mathematician Pierre-Simon Laplace said that probability was common sense reduced to calculation. And what he meant by that is that many of these things are going to feel intuitive to you. You know that when you flip a coin, you have a 50-50 chance of getting heads or tails. You know that your probability is 1/2 of flipping a head. That's your common sense. But we're going to find a way to quantify that. We're going to find a way to make it a calculation so that we can talk mathematically about the things that make sense to us and make sense of the things that confuse us. So let's start with terminology. And the first thing you need to know is that probability is the measure associated with how sure we are that things will happen. And what that means is it's a percentage, basically. A probability is a percentage, a relative frequency, a how likely things are to happen. And we're going to talk about probability in two different ways. We're going to talk about it in an empirical way, meaning things we've calculated, and we're going to talk about it in an observational way, things we've seen. And things that we see are generally the result of experiments, and an experiment is a situation that is controlled in order to produce an outcome. And the group of all of those possible outcomes is called our sample space. So our ultimate goal is to create experiments and use the sample space of the outcomes of those experiments to make decisions. Because the thing we care about is the event, the combination of outcomes that we're looking for. Meaning that you roll a die, the sample space would be the numbers 1, 2, 3, 4, 5, and 6. If our event was rolling an even number, the event outcomes would be 2, 4, and 6. Probability is really, in the long run, a long-term relative frequency of an outcome. So think about flipping a coin. Now you intuitively know that if it's a coin and you flip it and there's not something odd about it, that 5 out of 10 times it'll be heads and 5 out of 10 times it'll be tails. But like we did before, a few weeks ago, remember we did that experiment where we flipped coins? You'll notice that it didn't always turn out that way. That it's possible to flip a coin 10 times and get all heads, or to flip a coin 20 times and get all tails. It's unlikely, but it's possible. But if you flip a coin enough times, if you flip it 100 times or 1,000 times or 1,000,000 times, eventually, in the long term, the probability will turn out to be what you expect it to be. The experimental probability will match the empirical probability. Probabilities are always between 0 and 1. They are decimals, they are percents. Things cannot be negatively likely to happen, and we can't say with 180% certainty that something will happen. So we want to make sure our probabilities are always decimals, and they're always between 0 and 1. Things that are equally likely mean just exactly what they sound like. That when you flip a coin, both outcomes are equally likely, meaning they both have the same probability of occurring. And a fair device is one where all the outcomes are equally likely. If we flip a fair coin, that means it's exactly a 50-50 chance of each. If we roll a fair die, it means it's not weighted in one way or the other. It's not more likely to give you a 4 than a 2. Biased outcomes come when things are not equally likely, that you are not given the same opportunity to get one outcome as another. We're going to talk about probability almost exclusively in symbols from this point forward. And that symbol, that P with the A in parentheses, is the probability of event A occurring. That's how we designate it, P for probability. If the probability of event A is 0, that means there is no chance, regardless of circumstances, that A will occur. Meaning that if I roll a 6-sided die, I am never going to get a 9. The probability of that is 0. If the probability is 1, then event A is certain to occur, that there's no way anything else could happen. If I flip a coin, I'm going to get a heads or a tails. There is no possibility of me getting a neck or an ear or an elbow or any other possible outcome of that coin. When we say the probability of A or B, that means we are testing, say, event A. When you roll a 6-sided die, the probability of event A is getting a 2, and event B is getting an odd number. So we would count multiple outcomes for that. We would say we could get a 2 or a 1 or a 3 or a 5, and all of those are okay with us. That's what A or B means. A and B means they both happen at the same time. The complement of A, the probability of the complement of A, is the same as saying, what's the probability of anything that's not A? Complement of A and not A mean the same thing. So, if I'm rolling a 6-sided die and A is even numbers, then not A would be odd numbers. If A is getting a heads, flipping a coin, not A would be a tails. If rolling a die and getting a 1 is A, then not A would be getting 2, 3, 4, 5, or 6. And the probability of A plus the probability of not A is always going to add up to 1. Because if it's not A, it can't be A and not A and some other possibility. They have to encompass all the possibilities. And we call that the complement. Not the complement, you look super nice today. The complement, like two things that go together, that complement each other. When we talk about conditional probability, it's written there with the A and the bar in between them, A and B with the bar. We call that thing a pipe in computer programming. When we write that, we say the probability of A given B. And what that does is gives us the probability of event A occurring, given that we already know B is true. So, for example, what is the probability of picking someone in our classroom, given that we already know it's a guy? Or the probability of finding someone under the age of 16, given that we already know it's a junior. Our given probability changes the outcome, and you can see that in the formula. To find the conditional probability of A given B, we would take the probability of both events occurring, a person being under 16 and a junior, and divide that by the probability of a person being a junior. And we will explore that way more later, so don't worry about it yet. So, let's do an example and see what we can do. So the sample space, S, is the whole numbers starting at 1 and less than 20. So our sample space would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Notice, we don't want to include 20 because 20 is not less than 20. 20 is equal to 20, so be careful there. And we're going to define event A to be the even numbers and B to be the odd numbers. So let's separate though. And I don't think you need me to write them all. So A is going to be things like 2, 4, 6, blah, blah, blah. And B will be things like 1, 3, 5, same deal, blah, blah, blah. So what is the probability of A? If we were going to take the numbers starting at 1 and less than 20, how many of those numbers are even? Well, you'll notice, if we look at our list, 2, 4, 6. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of our numbers are even. So our probability would be 9 divided by 20. If we wanted to put that in a calculator, that would be equal to 0.45, I think. Okay? And are there 20 numbers? There are only 19. Let's check them. 4, 5, 6, 7, 8, 9, 10, 11, 12. There's only 19 numbers. So that would actually be 9 out of 19. And I don't know what that percentage is off the top of my head. Sorry, guys. Okay, and the probability of B then would be probability of not A, right? Because this would be the same as us saying the probability of not A. And that would be everything else, 10 out of 19. What if we considered event A and B? Are there any numbers that are both even and odd? Certainly not between 1 and 20, and not anywhere in math. So there aren't any numbers in A and B. So it's what we call an empty set. There's nothing in there for us. What about A or B? Well, that would include everything. So if we were going to make the set of A or B, we would do it the same way we've done everything else. And it would include all of those numbers. So, what is the probability that something is A and B? Of course, that's going to be 0. There's absolutely no way for a number to be even and odd at the same time. The same as the OR. There are no other options. A number cannot be a whole number and be neither even nor odd. So the probability of being A or B is going to be 1. A complement, we talked about that before. That would be everything that's not even. And the things that aren't even are the odd numbers. Things like 1, 5. And the probability of not A would be the same as the probability of B, which was equal to 10 out of 19. This is a trick question. The probability of A plus the probability of not A is always, 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 regardless of what A is, 1. So, what's the probability of A given that it's B? Meaning, what's the probability of a number being even given that it is odd? Of course, that should be 0. And the same with B. What's the probability the number is odd given that it's even? And that is 0. So how about these ones? Example 3.3 in your book. The OpenStax book is on page 169. The table below describes the distribution of a random sample S of 100 individuals, organized by gender and whether they are left-handed or right-handed. So they asked 100 people. So please notice, did they ask the same number of men and women? Something to keep track of. So what's the probability that someone is male? So that would be 43. Let me put some parentheses so it makes sense to you. 43 plus 9 divided by 100. 43 plus 9 is 52. So the probability the person is male is 0.52. The probability then that a person is female will be 44 plus 4 divided by 100, which is 0.48. The probability that a person is right-handed will be 43 plus 44 divided by 100, which is 0.87. And the probability that a person is left-handed is much lower, 9 plus 4 divided by 100, which will be 0.13, which is pretty close to on par with the general population. In the United States, about 10% of people are left-handed. So what's the probability that a person is male and right-handed? Well, that only includes people in this column right here. So it will only be 43 out of 100, which is 0.43. Probability a person is female and left-handed will only be people in this group right here. That'll be 4 out of 100, which is 0.04. The probability that a person is male or female, in our situation, there aren't any other options, so that would be 1. What's the probability that a person is male or right-handed? So that would include this box because they're male and right-handed. That would include this box because they're male. That would include this box because they're right-handed. So it would only leave this one. So it would be 43 plus 9 plus 44 divided by 100, which is 0.96. Now you'll notice a much easier way there would be to find the complement, to find out how many people are neither male nor left-handed. And in that case, there's only 4 of them, 4 left-handed women. What about the opposite? What's the probability that a person is female or left-handed? Let's think about this as the complement. There's only one group right here, this 43, that is neither female nor left-handed. So it would be 1 minus 43 over 100, and that is 0.57. What's the probability that a person's not male? Well, not male would be the same as the probability of female. Sorry about that. And we know that from above is 0.48. Okay, what about the probability that a person is right-handed given that they are male? So let's consider how many males we have. Remember, it's the probability of both divided by the probability of the second. So this would be the same as the probability of being right-handed and male, which is 43 out of 100. Divided by the probability of just being male. In this case, that would be 52. 52 out of 100. So that would be equal to 43 divided by 52. Okay, so let's talk about the probability of being female given that you're left-handed. So we want to take the probability of being female and left-handed, 0.04, divided by the probability of being left-handed. And if you see that from above, remember that that was 0.13. So the probability of being female, given that you're left-handed, is just about 31%, 0.31. So even though only 48% of our population was female, given that you're left-handed, only 31% of females are left-handed. Let's think about it in the other direction. What about the probability that you're left-handed given that you're female? Well, the top number stays the same. The difference is the bottom number. Then instead of using the probability of being left-handed, we're going to use the probability of being female. And that gives us a very different number, 0.08. So please remember that order matters. We're going to stop there because that's a lot of information already, and we'll pick up tomorrow with independence. If you have any questions, please ask me in class tomorrow.